Welcome to 6502 Assembly Language Programming. In this video, we'll investigate addressing modes. With its 11 addressing modes, the 6502 compares favorably to other CPUs of its generation, such as the 8080 and the 6800. Without adding much complexity, these addressing modes are a boon to game developers, enabling more compact and faster code. Before going into each addressing mode, let's look at the LDA and LDX instructions to see how the modes are specified. There are 8 addressing modes available to the LDA instruction. Looking at the source specification column, where it shows an example source line for each addressing mode, you can see that each mode has a very specific syntax. The assembler determines the addressing mode and hence the opcode from the source code syntax and the value of the operand. For instance, here you have an LDA from hexadecimal 80. Here you have an LDA from hexadecimal F238. Now, in the first instance, the assembler picks 0-page addressing mode because 80 is less than 256. And in the second instance, the assembler picks absolute addressing mode because F238 is way bigger than 256. As you can see, the LDX instruction has fewer addressing modes than the LDA, but the assembler picks the addressing mode based on the same considerations. Although many addressing modes involve the accumulator, in this addressing mode, only the accumulator is involved.
Implicit addressing involves an implied source or destination of data. There are 3 categories. Stack. These instructions either push data onto the stack or pop it off. Processor status word. These instructions affect individual bits of the processor status word. And register. These instructions feature registers as the implied source or destination. The 6502 conditional branch instructions use relative addressing. If the CPU evaluates the condition as true and takes the branch, it will add the 8-bit relative displacement to the program counter. The displacement can be positive or negative, ranging from negative 128 to positive 127. With immediate addressing, the data is embedded in the instruction itself. Prefixing an operand with a pound sign signals that the operand is an immediate value. In this example, the LDA instruction loads the value hexadecimal 25 into the A register. With 0-page addressing, an 8-bit 0-page address is specified by the instruction operand. Here's the address. It addresses this area of memory, or this location of memory, and the contents go to the A register.
To specify 0-page index addressing, code a 0-page address. Oh, pardon me, let me get a red pointer. A 0-page address, a comma, followed by an index register. Now the LDA instruction only supports this mode with the X register and not the Y. During execution, the CPU adds the contents of the X register to the 8-bit operand to form the effective address of 92. The CPU then loads the contents of that location into the A register.
Absolute addressing uses a 16-bit value as the effective address. To use absolute addressing, code your instruction, here a jump, followed by a label or numeric destination. During execution, the CPU loads the 16-bit value, which is Fox09 dog, into the program counter, and the execution continues from that place. The format of the address up here is Little Endian, sometimes called low-high. As you probably know, in this format, the first byte is the low order 8 bits of the value, and the second byte is the high order 8 bits of the value. To use absolute index addressing, code your instruction, followed by a 16-bit address or label, a comma, followed by an index register, either X or Y. During execution, the CPU adds the 16-bit operand to the contents of the Y register, forming the effective address. The contents of that address are loaded into the A register. To use indirect addressing, code a jump instruction, followed by a 16-bit address or label within parentheses. The 16-bit operand points to the low order byte of a 16-bit address. The CPU loads that 16-bit value from memory into the program counter, and execution proceeds from that point. To use index indirect addressing, code the instruction followed by a parentheses, a 16-bit value or label, a comma, an index register, and a right parentheses. The zero-page operand specifies a table of 16-bit values. Here it's 84. If you look at 84, there's a series of 16-bit addresses. The CPU indexes that table with the index register and loads the 16-bit value there, here F372, forming the effective address. Then the CPU would load up the A register with the contents of that address.
To use indirect index addressing, code the instruction followed by a left parentheses, followed by a zero-page operand, close parentheses, comma, and an index register, which is always the X register for this addressing mode. The zero-page operand designates the first byte of a 16-bit value in storage. During execution, let me get a red pointer. No red pointer yet? Okay, red pointer, yay! During execution, the CPU adds that 16-bit value to the contents of the X register to form the effective address, which in this case, in this example, is Fox452, right here. And so the contents of that location are loaded into the A register. Let's go to the IDE to look at some of these addressing modes. If you've never used the 8 bits and 1 byte IDE before, there are links in the description to tutorials about the IDE and about how to load and save your work. There are 2 exercises associated with this video, so let's get to it. Here we are at 8bitsand1byte.com. Let's go ahead and navigate to the source code. I have work in progress, so we're going to resume. And now we're interested in ex6.asm. So let's have a look at our goal that we have to accomplish in this exercise. It's pretty simple. We need to use the 8-bit value in param 0 to index the table referenced by the 16-bit value in word 0. And the idea is to use indirect indexed addressing. In this addressing mode, the CPU will load the contents of that memory address and add the index register to that to form the effective address. So let's look at our 6502 instruction reference to get another recap of that. So here we have it, indirect indexed addressing. And it says the instruction contains the 0-page location of the least significant bit or byte of a 16-bit address. The Y register in this case is dynamically added to the value to generate the target address. Paraphrase. And here are 2 examples. And note the syntax where you have the base page address or label in parentheses followed by a comma followed by your index register designation. Okay, so I think now we know enough to code the solution. So let's get to it. Now, before I go ahead and start coding, I'll give you a moment to pause me and try it yourself. Well, welcome back, or let's continue, whichever is appropriate. First thing I'm going to do is change this to implemented and click run. So now you can see we have a status light here changing from yellow to red. So our goal is to get this red light next to the W to get it to change to green. So let's go back to the source tab and start coding. So you want to load an index register in from param 0. So we're going to go LDY, let's go lowercase, LDY param 0. And now we're going to address the table pointed by inward 0. So we're going to go LDA parentheses inward 0, comma Y. And now we're going to store that in the output. In output 0. Okay, pretty simple, and that should do it. So let's go look at our output pane. Aha! So we have indeed changed this indicator to green, indicating success. So let's go ahead and have a look at that. We're going to find ex6 here, put a breakpoint down. We're going to step over this. So here we loaded Y with param 0. So if we look at the Y register, we have changing to base 10, we have the value 5. Here we'll step again. And now we index the table, and the A register should have a value from the table. But let's go find this table and see what it looks like. So if we look at the log pane, it shows our memory, and we know that inward 0 is at 84. That's here. And this, of course, is this 16-bit value is in low-high or little endian format, and it's F317. Well, that is not a RAM. That is up here in read-only memory with the code. So we're going to go find it. I'm just going to do a find, and that was F317. Okay, and here is our table. You can see it's just a table of bytes numbered 0 through 9. So if you index this with 5, you should actually get the value 5. That's what we would expect in the A register. And so looking at our CPU tab, we indeed have the value 5 in the A register. Okay, well, let's do another step, and I'm going to clear this breakpoint and just hit run or resume and let it go. Okay, so we successfully solved the first exercise for this video. Let's move on to the second exercise and have a look at ex7.asm. Once again, the first parameter is an index contained in param 0. The second parameter is a 0-page address of a table of 16-bit pointers, which is at inward 0. Since the solution to this exercise involves indexed indirect addressing, let's look at that addressing mode in the reference. So it says it's normally used in conjunction with the table of addresses held in page 0 or 0 page. The address of the table is taken from the instruction and then added to the X register to give the location of the least significant byte of the target address. So it's going to add the X register to this address, in this case hexadecimal 40, and then that gives it the address of the 16-bit value. The CPU will load that address, and then that is your effective address for the instruction. So that is where, for instance here, the LDA will happen. It'll load A from that address. Or in this case, the second instruction stores A at that address. Note the syntax is somewhat different for indexed indirect than for indirect indexed, because the register is specified inside of the parentheses rather than outside. Okay, I think we know enough to code our solution. So if you want to pause me now and have a go, feel free. Okay, welcome back. First thing I'm going to do is get rid of this not so that our test fails. So scrolling down to the output pane, you see this nice red light next to the O, and so we want to make that turn green. So we're going to scroll up, go back to the source pane, and start coding. So we want to load, lowercase, load X from param_0. That is our index. And then we're going to immediately index this table. And this will load the right value into the A register. Then we're going to store that at output 0. Okay, let's run that. Okay, so we do have a green light next to the O. And so let's go have a closer look at that exercise. Let's walk through it. And, oh, wrong place. Okay, I'm going to try this again. EX7. Okay, I'm going to put a breakpoint here. So we're just going to step through this. So looking at the registers in decimal, you can see that X has a value 4 in it. And you can see it's going to index this table at inward 0, which is at 84, which is a base page address, or 0 page. So that's here. And if we're addressing it, if we're indexing it with the value 4, like 0 would be here, 2 would be there, and 4 would be here. So you'd expect that it would be loading up whatever is at F375. Again, that's location in code. Let's go find it. Let's see if we can find that. Oh, here we are. Okay, so we should have a value of 33 in the A register. Oh, so we do. So everything is working as expected. So just to recap, we had this table in the base page, or 0 page, excuse me. It's a table of 16-bit pointers. Each one of those pointers points to one of these elements here. And so the instruction indexes this table to get to the contents of this table. Very fancy. Okay, so I think that wraps up this video. I do hope that you gained some benefit from it, and I do appreciate you very much for watching it all the way through. You have a great day. Please don't forget to like and subscribe.